Hello everyone, I'm Chen from the University of Pennsylvania. Here, I'm going to introduce you to our Python package called BABS, which is reproducible, generalizable, and scalable software for BABS analysis of large-scale datasets. I have no disclosures. There have been a lot of reports that warn people on the reproducibility crisis in the neuroimaging studies. There are numerous choices in both image processing and statistical analysis. And it turns out that even with the same data, different analytical methods and tools can lead to discordant results. An example would be this Nature paper in 2020. There may be two ways to address this reproducibility issue. First, we can increase the sample size to enhance statistical power. However, on the other hand, this also increases complexity and heterogeneity in the dataset. In addition, we can also record very detailed descriptions on methods and protocol. So we are wondering, are there tools that can help us automatically track all the data provenance? There are indeed several existing methods and tools for enhancing reproducibility. We can use portable containers like Docker with Singularity images that wrap up dependent packages. BABS are containerized software that can be applied to the standard BABS data format. BABS also read metadata in the setcard JSON files in the BABS dataset, and in this way, it can automatically configure the correct processing workflow. Applying containerized BABS enhances reproducibility. However, only with containers, some data provenance are still not automatically tracked. For example, what input data was, which version of containerized software was used, and how it was applied. It is very difficult and painful to manually track all this information, especially for a large dataset. Therefore, version control tools are essential here. Just like Git for code version control, DataLad, which wraps up Git and Git Annex, is designed for data version control. To make the workflow scalable for large datasets, the DataLad-based Very Big framework was proposed for reproducible processing of large-scale datasets. This enables automatic and scalable track of all data provenance. However, there are several drawbacks in the current implementation of the existing solutions. As you can imagine, there are a lot of different data analysis tasks. For example, input BABS data can be single session or multi-session, and it can be raw BABS dataset or BABS derivatives. In addition, there are various BABS apps too, including QSA prep for diffusion MR data and iFormat prep and XCPD for iFormat data. Furthermore, there are more than one cluster job scheduler systems, such as SGE and Slurm. The commands for the same purpose, like job submissions and status checking, are different across clusters. So there are a lot of combinations here, and our lab's previous protocol is to have one script per combination, so we have accumulated a lot of scripts. This poor generalizability of the implementation makes it very hard to version control the scripts. In addition, the implementation of the Very Big framework involves numerous steps and functions, making it hard to debug and not friendly to the beginners. This motivated us to build a Python package called BABS, or BABS App Bootstrap. It is a reproducible and generalizable software workflow for analysis of large datasets with BABS apps. It makes the data processing reproducible because DataLad is used to track all data provenance. It's scalable because Very Big framework is adopted. It's generalizable to different use cases, including different BABS datasets, different BABS apps, and is compatible to popular cluster systems like SGE and Slurm. Finally, it's user-friendly because BABS automatically performs the bootstrap. Here, bootstrap means to set up scripts for data processing and provenance tracking and execute these scripts. BABS follows the workflow of fairly big framework. The real store here is a permanent storage space on the cluster, and the input BABS dataset locates in the input real store, whereas the results will be deposited into the output real store. The subject-specific data will be cloned to an ephemeral or temporary compute workspace and processed with the containerized BABS app with the parameters for executing the BABS apps defined by the user. The jobs will be submitted to a cluster compute node. The results will be zipped and deposited into the real store, and BABS will iterate across all the subjects and compute their jobs in parallel. After all jobs finish, the results will be merged. And along the process, the full audit trail of the successful jobs is also saved in the output real store. BABS features several functions which can be called from the command line. Users need to prepare input datasets and containerized BABS apps in data-like datasets format. They also need to provide a container's configuration YAML file that defines how the BABS app will be executed. With these inputs, BABS init will initialize a BABS project. And then users can use BABS check setup to check if this BABS project has been correctly set up. Next, users can iteratively call BABS submit and BABS status to submit jobs and check job status. Failed or pending jobs can also be resubmitted if needed. Finally, after all jobs finish, BABS merge can be used to merge the results. Now, users can consume the results by cloning out the output real store as another folder. Here we list several example use cases of BABS. BABS is currently compatible with BABS apps such as AlphaMapPrep, QSAPrep, and XCPD. In addition, it is compatible with different input BABS datasets, such as raw BABS dataset, the BABS derivatives like AlphaMapPrep results, or even more than one input BABS dataset. Finally, BABS currently supports SGE and SNRM's HPC systems. We provide an example walkthrough of BABS publicly available online. In this walkthrough, we used some toy BABS app that counts files in the subjects folder and a toy BABS dataset for demonstration of BABS functions. We encourage new users to go through this walkthrough. We also provide an example YAML file for this toy BABS app. In this YAML file, we define the arguments in the singularity run command, the output folder names to be zipped, and the BABS app version to be included in the zip file names. Importantly, we define how much cluster resources it needs and the necessary commands to be run first, for example, activating content environment. We finally define the path to the temporary job compute space. Different clusters would have different setups. The lines highlighted in yellow require users' customization. As a showcase, we applied BABS to a large-scale dataset, Healthy Brain Network, or HBN. It is a single-session dataset, including over 2,000 of subjects with T1 weighted images. AlphaMapPrep anatomic workflow was applied. We went through all the BABS functions to reproducibly process this large dataset. Here, we like to highlight the functionality of BABS status. This figure shows the example printing messages from BABS status after all jobs have been submitted. Here, each job corresponds to a subject. BABS status first summarizes the statuses of all jobs, including number of jobs submitted, successfully finished, pending the queue, running, and fail. In addition, it also audited failed jobs. It summarized how many jobs have alert messages in the log files. And these alert messages are predefined by the user in the container configuration YAML file. These alert messages would help debug what's wrong in those failed jobs. For those jobs without alert message, BABS performed further job accounts and summarized the information here. Regarding the software development and release, the source code of BABS has been version controlled and publicly available on GitHub. continuous integration or CI testing has also been used to ensure quality and stability of BABS. Users can install BABS from PyPy platform. We also provide comprehensive BABS documentation available online. In summary, there are several challenges in processing large-scale neuroimaging datasets, specifically the complete reproducibility, scalability to large datasets, and the generalizability to different use cases. To address these challenges, we built Python package called BABS for reproducibly processing BABS dataset at scale using BABS. It automatically tracks all data provenance and is scalable, generalizable, and user-friendly. BABS cannot be built without massive collaborations. I'd like to thank all collaborators in this project. And thank you for your attention.